Hey everyone, welcome back to Computer Science 4303. Today we are doing lecture number 6, which is on grid algorithms. So last time we talked about space representations, the first lecture on space representations, and we talked about grids in depth. And now we're going to talk about some of the algorithms that we can use on grids, specifically on grids and possibly not on other data structures. And the reason we want to do that is because in assignment 2, we are going to be writing our own pathfinding system using vector fields for pathfinding. And we will be using the algorithms that we are looking at today in that assignment. But first, before we get into the old boring math, I wanted to change it up a little bit today and show the motivation for a lecture like this. So let's switch scenes over here. And who can tell me what game I'm playing right now? Anyone out there play this game or part of the Discord server where I announced that I would be playing this? Someone out there in the chat has to know the game. Path of Exile, there you go. So forgive my low level in the game. I started playing the new league about 2 days ago, so I'm only level 60. I used to be pretty into the game and like speedrunning, leveling and stuff, and it was really fun. But I haven't played it in probably 2 years now. So what we're going to do is I want to show you some of this game because of its pathfinding. And in this game, we really have a good example of why you can't use the standard algorithms for pathfinding for things like A star, etc. So, as you can see here in the game, I'm in one of the first towns in the game here. Up in the top right, I've got a mini-map of the town. And in the mini-map, if I press the tab button, my mini-map actually overlays where I am on the screen. So this is my position here. If you look at this little X, that is my position in the game. And the light blue outlined colors here give the details of the map. And so I'm in a town right now, which is one of the simpler maps. But you can see that, for example, if I walk over here, then I'm right up against this wall on the mini-map, and you can see that, yes, I'm indeed like in this little corridor where I can't pathfind beyond these walls. And that's represented here on the mini-map. So, in this game, you can bind pretty much any of your keys to do all of your different abilities. So if I move my camera up just a little bit here, so it's not blocking the ability bar, down here, you've got all your different abilities. So some of these are like different attacks and different buffs and stuff like that. But you can see here that you can also bind the movement key to pretty much anything. So right now, if I left click somewhere, then I'm going to move to that location. So this is really simple case, right? Where I'm out in the open and I'm clicking and my character is just running straight to a particular area. But if I open up the map here again, and I say, for example, okay, on the other side of this like rocky area, there is a place that I can walk down here. So if I left click down there, then the pathfinding system computes a path to that location and will walk my character to that location, right? It doesn't just try and walk me straight to that location, because if it did, it would walk right into the wall, right? So there's definitely some smart pathfinding going on here in some form. Again, so you can see here by the mini-map that there's this little outcrop here that I cannot walk in this area, but I can walk on the stairs. So if I click up on the stairs, my character will walk around. So there's obviously some sort of pathfinding going on. However, in a game like this, I think that the player's pathfinding is probably the least interesting pathfinding in the game. And why is that? I forgot to also mention that you can hold down the left mouse button and it will just follow your mouse cursor around in real time. So there's some sort of dynamic pathfinding going on there too. So some people said, you know, like this is, someone in the chat said this is very similar to League of Legends. It's also very similar to games like Diablo, and that's all true, right? Any kind of game where it's like a top-down action RPG or MOBA, you're going to have this sort of movement system. So you really do have, like, even though the game world looks a little bit 2D, it looks a little bit 3D and your character models are drawn in 3D. It really is a two-dimensional map, right? So all of the pathfinding here is going to be done in 2 dimensions rather than 3 dimensions. So we can talk about some of the algorithms that we might use for this. But as I said, so what is the problem here? In terms of the problem that we looked at for player movement a couple of lectures ago, here we've got the problem is single agent, right? Because there's one player. It's a static environment, right? Because nothing in the environment is actually changing in Path of Exile, as far as I know. Like a door may open or close, but that's about it. But I actually don't think that affects the pathfinding system, but we will actually go test all of those things. And I haven't done these tests yet, so we'll figure out together as we go what we think the pathfinding engine is actually doing. So this is single agent, single goal, right? I've got one agent here, which is my player character, and I've got one goal, which is the place that I'm trying to click. And it looks to me like when I click, it's using distance as a cost, right? So remember, whenever we do pathfinding, we are trying to minimize some cost. And that cost could be like damage taken if you're playing like a tower defense game, but I'm pretty sure this is actually minimizing distance. And I think I know that 100% sure, because if you click somewhere and it will actually run you through a hazard on the ground if there is a hazard on the ground, right? So maybe that's part of the game design. Would the game be more fun if you clicked somewhere and it would avoid all the hazards and avoid all the spikes? Maybe it would, maybe it wouldn't, right? So let's go look at an example of NPC pathing. So we're in a town right now, and in the towns, as far as I know, from when I've played the game, all the NPCs are static, right? So anyone with a name over their head here, that's a static NPC. You can purchase things from them, you can sell things to them, etc. But we're not super interested in static NPCs. We're concerned with more of the dynamic NPCs that you kill throughout the game. So let me go down here. This is the teleport pad where I can teleport to various places in the world. And like I said, I've only got like 4 or 5 hours in this, so I'm only up to like Act 7 right now. But I've still unlocked a number of places that will be interesting for us to explore. So first, let's go to the second place you go in the game, which is called the coast. So this is like a level 1 or level 2 area where not a whole lot is actually going on. But we can walk around and we can see some of the NPCs. So we can see here that our map is a little bit more complicated than the one in the town. We're under a fog of war, right? So as we explore the map, you can see this boundary here. That's the boundary that I've explored the game. So that boundary continues to grow as we walk around, and you can see here a bunch of different enemies. And those enemies, pretty much every single enemy in the game is trying to get to me, to kill me. Right? So here you can see, let me just remove the mini-map, that all these enemies here, I can hover over them. There's some drowned and cannibals and whatever. And they're all trying to hit me. I'm level 60, they're level 1, so they're probably not going to do any damage to me. So if I click down here to pathfind, you can see that all of those enemies, and these are really slow-moving enemies, they will move to try and get to me and hit me. So that doesn't seem too bad, right? Maybe we could do 4 or 5 or 6 calls to A-star pathfinding that we learned in the prerequisite for this course. But let's walk around and see if we can get sort of a better example of the things that can happen in this game. So we'll walk up here. Oh, here's a bunch of enemies. But look at this. Okay, now we've got about 30 enemies on the screen. And they're all trying to get to me somehow. They also collide with each other, right? So for example, these crabs are trying to get to me, but they can't reach me because there's so many enemies in the way. So there's also enemies up here trying to get to me, etc. They're trying to hit me. They're taking a little bit of my shield away, but not a whole lot. So let me just blink out of here, or dash out of there. And now you can see that as I'm running around in real time, all of their paths are changing, and they're all trying to get me, to surround me, to kill me, right? So let's just stand over here. This is just a cosmetic fire. It's not actually doing damage to me, the one I'm standing on. But you can see that now I can't even pathfind around these things. So here's a good example to figure out what sort of pathfinding system it's using. In my opinion, the pathfinding in Path of Exile is not it's not taking dynamic changes of NPCs into account, okay? So, for example, if I'm over here and I click on the other side of these zombies, it will try and walk through the zombies to get there, right? So it's using the level geometry to pathfind, right? So if I'm down here and I click up here, well, in some cases it uses level geometry, in some cases it doesn't, and I'll show you examples of that. So if I try and click over here, sometimes it tries to avoid enemies, but it gives up after a little bit. Like, it didn't walk around this large path to get over there. So it's not really taking NPCs into account in its pathfinding engine, just the level geometry. So we've got a bunch of enemies here. They're trying to kill us. They're walking around in real time trying to get to us. And you can see that indeed some of them will go around to the other side to try and surround us eventually to get to me. But let's kill all these, and we'll see what our pathfinding system is doing. Okay, so here, if I look at the minimap, there's this wall, right? I'm up on this little cliff, and below me, there's this lower ground. So I can't walk. If I click, it's not finding a path from where I am to where I want to go, which is down here. I'm not sure if you can hear the mouse clicks, but I'm definitely clicking there. But watch this. If I go down here, and now I can sort of see the path down here. If I click over here now, where I just wanted to go, but couldn't go, now it will pathfind me around to that area. So what the hell is going on here, right? Well, what's going on, I think, now this is just me as someone who has written this sort of search algorithm before for pathfinding, making guesses at this. I hope there's no, well, it'd be cool if there was some Path of Exile or Grinding Gears people in the chat. But if I think what's happening is the following. Just watch. So this level is huge. Some of the levels in this game might take like minutes to traverse, right? So by levels, I mean like areas or zones, which are separated by doors, which then you load the next zone. So again, if I'm over here, you can see that in order for me to get from here, where I am, to up here, what I've got to do is I've got to go around, down to the ramp, and all the way back up. So let's see if it does that. Well, I'm going to click here. It runs into the wall and can't get there. Okay? But if I'm down here, just one more example of this, if I can see the path and I click up here, oh, look at that. That time it didn't do it. It just ran into it. So I'm clicking up here now and it's not taking me there. What if I'm right here and I click up here? Nope, not doing it. It looks like if I'm down here, it's not... Okay, there, look. So we found some threshold where the path works versus the path didn't work. So if I'm standing here and I click up near this rock, it will run into the wall, right? Stupid path. It tries to get there but doesn't. If I go a little bit down further and click up next to the rock, it does the pathfinding. So what the hell? What's going on here with this video game, right? Why is it stupid in some cases, and why is it smart in other cases? Well, what I think is going on is that it somehow uses your vision or a radius around the player to do that sort of pathfinding, okay? So obviously, if I want to get from here up to here, it should walk around like that. But if I'm a little bit up too far, right? Like if this entrance is too far away, then it does oh, okay, so that time it worked. What if I'm up here? Okay, so that time it did the dumb pathfinding. What if I go further away and then click up here? What the hell's going on with this game, right? So if I'm all the way over here and I click over here, now it finds the path. So, okay, maybe there's some weird pathfinding happening around the walls, right? So, let's see. What if I'm facing that direction and click over here? Well, it finds the path again. So why does it not find the path from here to here, right? If I click here, it runs into the wall. But if I'm over here, now I don't even know, okay? So there must be something going on under the scenes that has to do with like proximity to walls, proximity to ramps, right? So yeah, so someone in the chat just said maybe it has to do with like the sharpness of turning angles or something like that, or detours, right? Because if I have to go from here to here, then I have to make this sort of sharp turn around this, and that didn't work, right? Or maybe it has to do with the relative distance between my position and over here versus like the distance to the thing. I don't know. Maybe, you know, it'd be really cool if we could talk to someone from Grinding Gear Games, but this is something that, you know, I'm not sure how it works. But what I'm going to do is let's show some more kind of hardcore examples of some of the pathfinding. So let's go to a later act. We'll go to an area where there's going to be lots and lots of monsters, okay? So here we go. So the new mechanic in this league are these statues that you can go around. And I just want to find one of those because there's usually tons of... So look at this. We've got, I don't know, 50, 60 enemies around me right now. But what I'm trying to do is I'm trying to find one of these statues. Okay, there's a door to the next area. I don't want to do that yet. Of course, when I don't want to find... here's one. Okay. So look at the amount of enemies that are on the screen right now. There's got to be at least 100, right? And they're all pathfinding to me. They're all hitting me. They're all running after me. So, and they all seem to be finding a path. They're all going around these obstacles, right? But let me go around this obstacle here, and we'll try and find an example. No, that's a zone line. Okay, so let me get up here. Here we go. So if I go around this corner, how many of them will actually come to me? Oh, look at that. Okay, so the enemy pathfinding has something to do with vision or obstacles, right? Because here they're all trying to get me. They can see me. They're all going through that door, right? Here I am in the corner. They're all trying to get to me. These are all stuck. Oh, I almost died. So there's something going on, right? I just kill these all so I don't die now while I'm doing the demonstration. You just saw that when I stood around here, enemies around here either didn't see me or didn't want to pathfind me. But when I moved over here, now they can see me through this little crack, right, through the door, and they all came after me. So we've got a couple of questions here. Why is it based on vision? Well, that might be a game design decision, right? You don't want enemies to run toward a player if they can't see them. That sort of makes sense, so we understand that. But what I want to cover in this lecture is how in the hell are they doing 100 different pathfinding calls every frame of the game or every few frames of the game? Like, how is that possible, right? And so that's what we're going to do in this lecture. But first, I wanted to check a couple of other things like, okay, so for my pathfinding, if I'm in here, if I click out here, will it pathfind? I don't know. So let's click out there. No, it's running into a wall. Okay, let's see at what threshold the pathfinding starts being smart. So I'm going to click here, clicking here, clicking here. Okay, so when I got to about here, right, that's when it started to run around the wall. But if I'm maybe like out here and I click over here, it does the path. So there's something weird going on around walls with this pathfinding system. Maybe it has to do with like wanting the player to be able to pathfind neatly around walls. Oh, I know what it could be. Here's my new guess. So as I said, I can just hold down the mouse cursor. I can hold down button 1 and it will follow my player around. Okay? But what happens if I do the following? So if I'm using this method where I'm holding down the button and my mouse cursor goes onto the other side of this wall, do I want the player to actually go outside the wall? Or do I want them to run along the wall like that? Well, okay, it just went outside the wall. So it's all, maybe this is not a limitation of the pathfinding system, but maybe it's a game design decision where it says, instead of taking the long path around, like just run along the wall. So there's lots of interesting questions and game design decisions to be made when making a system like this, right? So that's just some. Yeah, it's not. I don't think it's a bug. I'm pretty sure that the Pathfinders at Grinding Gear Games would be able to do that if they wanted to, but for some reason they're not doing it, right? And just one more example of how crazy the pathfinding can get. Let's activate this shrine, and let's just see how many enemies spawn. Okay, this is one of the tamer ones, I think, but like I've seen like 200 or 300 enemies spawn from this thing. Right, so there's all sorts of cool stuff that you can buy here, but anyway, that's part of the game. Yeah, and so maybe hugging walls, someone said, is useful for avoiding enemies, so they want you to be able to hug walls, etc. But let's just do one more example here. We've got this little area where there's a tree, and so I can't run around this tree, but just watch. Okay, so I'm holding the left mouse button down, okay, and slowly moving my mouse over. And it's not pathfinding. Let's see at what point it actually does the pathfinding. Okay, at that point, it did the pathfinding. So it's not just a matter of algorithms. It's a matter of game design, right? If someone wants you to make the pathfinding for their game, there's going to be lots of different things going on. But for this class, again, I don't want to take too much more time on playing the game, but I'm sure more people would want to see me play instead of lecture. But the real thing here is, how do they get hundreds of units all pathfinding at the same time? So let me switch back over to the PowerPoint, and I'll exit Path of Exile, and we will start the lecture for this. Okay. So here we go. Now, if you did the prerequisite for this course, I think about a third of the class didn't. The first about third or half of this lecture is going to be a kind of a review, okay? We did these things during 3200, but they help us set up for vector fields, which is the thing that, well, one of the solutions that I would implement if I wanted to do the pathfinding in a game like Path of Exile. All right. So, grid algorithms. What are we going to cover today? So the first thing we're going to cover is something that I like to call connected states, and I'm sure you're all having flashbacks and PTSD about assignment 2 in Computer Science 3200, but that's all you can do. We're going to be revisiting some of those ideas today. So connected states means how can we tell if a path exists between 2 points on a map, right? So maybe I just want to be able to look up, can I get from this place to another place? And maybe I have a feature in my game that says, okay, if I can't move the NPC to the player, then don't bother doing any further calculations, right? So if I could get some really fast computation for how to look up paths between points on a map, or sorry, the existence of paths, then that would be great. We did that in 3200, but we're going to review it again today. The second question is, if a path exists, what is an approximate distance that you would have to travel to get from one point to another? And I'm calling that a distance map, okay? So a distance map, we're going to compute one, and it's very, very similar to the connected states computation, but it's going to allow us a constant time lookup for ground distance. So you could say, okay, this point is 15 distance away from the player, or this one is 30 distance away from the player. And then we'll finish off the lecture by talking about vector fields. And vector fields are built on distance map. And what we're going to have is a constant time lookup for all states' shortest paths to a single place on the map. So if you think about the Path of Exile example I just went over, that's what the NPCs are doing, right? So the NPCs, all of those NPCs are trying to get to one position, which is the player. And so if we could somehow come up with a constant time lookup for every place on the environment to get the shortest path to a single goal, which is the player, that ideally is exactly what we want, okay? Now, I'm not saying that that is how Path of Exile or Grinding Gear makes their pathfinding system. I'm saying that that is one way in which we could do a pathfinding system like that, and that is what we're doing for assignment 2. So in assignment 2, in my opinion, you are going to be writing a better pathfinding system than Path of Exile has. That's a strong statement, but better in terms of being able to solve more paths. without going into all of those design decisions. Okay. So what are connected states? Let's start off with connected states. So states, in this lecture, states are going to be places on your map. And when we're talking about grid algorithms, then a state is going to be a particular cell in the grid, right? So we've got grids. The grids are composed of equally sized cells. And so when I say a state, that means a particular cell. And so states or cells are connected in a grid if a legal path exists between them, no matter how long, right? So if I can possibly find my way from one area to another area, then that is those two states where I started and where I want to go are called connected. Excuse me. So a connected sector, I'm calling this a sector, is the entire set of states that are all connected to each other. Okay, and we'll show an example of that graphically. An important thing to note is that connectivity is transitive. So if state A is connected to state B, and state B is connected to state C, then that means that A is also connected to C, right? So if I can get from A to B, and if I can get from B to C, then I can get from A to C. However, that does not mean that the shortest path from A to C is to go from A to B to C, right? This is just talking about connectivity. I've got another comment on this slide that I'm going to skip over because it talked about object sizes, but we're not really, I guess we could talk about object sizes, but we're not going to go too far into it. But if we remember from 3200 that if you have different sized objects, they may or may not be able to go through different parts of the grid. Okay, so let's talk about grid connectivity. And this is, yes, it's a review of part of 3200, but it won't be that long. So we've got a grid here. And in this grid, just like in 3200, you can only move around within adjacent cells of the same color, okay? So I can move from this cell to the neighboring blue cell, but I can't move from this blue cell to this green cell. Similarly, I can't move from this blue cell to this gray cell, okay? So for example, this state here and this state here, they are connected. And they're connected because a path exists between them. And so if we want to talk about object sizes, we're not going to get in too much into object sizes in this course. But if you did have sizes that had to be taken into account in your grid, then an object of size 1 would occupy one cell. An object of size 2, if I can draw it here, would occupy 2 cells. So this is an object of size 2, and an object of size 3 would occupy 3 cells. So, for example, an object of size 2 could move from here to here, but an object of size 3 couldn't because it wouldn't be able to fit. Okay, so that's what I mean by object sizes. So these A, B, and C are all connected for size 1, but they are not connected for sizes 2. These are not connected for sizes 2 and 3, and the reason is because an object of size 2 or 3 would not be able to fit on this square, right? Because it would be overlapping 2 colors. These, however, are connected for size 2, because an object of size 2 would be able to move up here and along here to get to C, and it would be able to move here and then up to get to B. So, but these are not connected for size 3 because there's a width of 2 here and a width of 2 here, and so you wouldn't be able to fit an object of size 3 through that pass, okay? So, and similarly, these two are not connected, right? Because you can't, oh geez, excuse me. Got the hiccups. You can't move from here to here because there is no, you can't walk between blue and green cells. Excuse me, had to sneeze. So these aren't connected because you can't walk between different colored cells, okay? Not connected. So what do I mean by a connected sector then? So a connected sector, I've shown one here in purple. This sector is a group or a collection of cells that are all connected for size 1, okay? So that means that if it's colored pink or purple, whatever you want to call it, depending on your monitor, that I can path find between any of these cells, right? So any of these, I can get to any other one for size 1. Okay, So that's what a connected sector is. And so we are talking about the first problem, which is connectivity. So how do we compute connectivity? If you did 3200, you know how to do this already. But two states in our grid are connected if any four-directional path exists between them. And so if we go back to breadth first search, we can use a four-directional breadth first search to determine four-directional reachability, right? Because if we can breadth first search out in four directions from a particular location, if we eventually hit another state, so any state that we hit with that breadth first search is reachable from that initial location. So instead of computing separate paths, we're going to compute connectivity all in one pass, okay? And so the complexity of computing connectivity is going to be the number of states or cells in the grid. So however many cells you have, that's how many operations you're going to be performing. That's the time complexity of computing connectivity. So if you've got a grid with 100 by 100, however long one of your iterations of breadth first search takes, it's going to be 10,000 times that. So it's 100 times 100 for 10,000. So if we recall back in 3200, and just for, just to have it here for people who maybe didn't do 3200, I waved a lot of people into this course. We have this general uninformed tree search algorithm. And what this algorithm does is it tries to search the state space of a given problem, right? So for example, this uninformed tree search problem will search out throughout your environment in some sort of way using tree search. And I'll get a visualization for you in a bit. So what this algorithm does is the following. So you've got in your problem and your strategy. So a strategy would be something like a breadth first search or a depth first search. That's your strategy. And your problem here defines your environment. It defines your initial state, your goal state, your legal actions, etc. So just an uninformed let's search everywhere type of algorithm would say, okay, we're going to start off with an open list, and that open list is going to contain nodes, and that first node that you put into the open list is going to have the initial state in it. And then we're going to loop forever, okay, so while true. If the open list is ever empty, then that means I haven't reached my goal. And if I haven't reached my goal, then I'm going to return fail. So returning fail means no path exists. I have no solution for this. If the open list is not empty, then I still have nodes left to explore in the tree search. So I'm going to grab one of the nodes from the open list using some strategy, okay? So I'm just going to take some node from the open list, whatever that node may be. And whatever my strategy is, so if it's depth first search or breadth first search, etc., that's going to determine how I get that node from the open list. If the node that I pulled from the open list is the goal, then I've found a solution, okay? So what you do is you go back through the parent pointers. We did all of this in 3200 to find the path. And so if the node if the node that I pulled from the open list, if the state according to that node is the goal, then I have a solution, so I can return that path. Otherwise, if it's not the goal, then I expand that by adding all of its children to the open list. So we've done all this before, and how we turn general uninformed tree search into breadth first search is really, really simple. You all answered this question on the exam before, is that we use a queue for the open list structure, okay? So by using a queue, all we have to do to get nodes from the open list is we pop them. Otherwise, if it's not a goal, we push them to the end of the queue, okay? So in breadth first search, it's expanding by breadth, okay? So every new node that I add to the open list, I want to take out in a first come, first serve order, or first in, first out order. And that's what a queue does, first in, first out. So let's have a little look at a general breadth first search problem. So let's say I want to get from state A in this graph to state C, okay? So the initial node in my tree search is going to contain state A. And then what I'm going to do is I'm going to expand node A by creating more nodes in the search tree based on where I can go in this graph, okay? So from A, the legal actions are go to B and go to D. And so what I do in breadth first search is I'm going to expand the tree by putting nodes D and nodes B in the tree. And so this is the tree right here. And so then what I'm going to, and just to remind you all that over here, this is a search tree which contains nodes, and this is an environment which contains states. So nodes have additional bookkeeping, we all remember, like the G cost, the H cost, all that sort of thing, parent nodes, parent pointers. So after I've done this, so I've expanded the complete breadth at depth 1, now I go to depth 2. So I'm going to expand D now. So D can go to A, to B, and to E, like this. Then I'm going to expand B. So B can go to A, D, E, C. So I expand all of those. And then when I go and I expand the open list, or when I grab a node from the open list that contains C, then we've found our path. So that's how breadth first search operates on a graph. We all know that. Here's how it operates on a grid. So I'm going to start at a particular location, and then I'm going to expand outward and outward and outward. Okay? So that's how breadth first is going to look in a grid algorithm type setting, or a grid space representation, with 4 directions. Okay, so just a reminder, breadth first search is complete. So we've got a number of properties on each algorithm that we want to look at. Breadth first search is complete. So that means that it will explore the entire tree, so it will find the goal node if it exists, right? So what that means for us is that if we use breadth first search, we are guaranteed to find a path if a path exists between 2 nodes. So that means we're guaranteed that our connectivity computation will be correct. And breadth first search, it won't necessarily find, well, I won't get into that yet. It will find the shallowest goal node, since it explores all nodes at a given depth before the next step. Okay? So, what does that mean? Well, if we look over here at our sample breadth first search, the first time it found the goal node, the path it took was A to B to C, right? So that's the shallowest goal node in terms of the number of actions. But if our actions have costs, and we're trying to minimize costs, is that the shortest path? Can someone out there in the chat tell me the optimal path in terms of the sum of the action costs to get from A to C? Okay, someone out there is awake. Thank you, Pale Blue Zebra. So they said go from A to D, D to E, and then E to C, right? So ABC had a sum of 11, and ADEC had a sum of 7. So breadth first search will find a path, okay, if one exists, but it is not optimal in action cost. It's optimal in the number of actions, but it's not optimal in action cost. So, in general, and in general means that all the time, sometimes it might find the best path, but in general, it does not find the best path. It does not produce optimal solutions, since the shallowest node is not necessarily optimal, right? Breadth first search is optimal if path costs is a non-decreasing function on depth. So that's kind of complicated, but what it usually means in practice is that breadth first search is going to produce optimal paths if the action costs are all the same, right? Because if we look back at our graph, if we had all of these as 1, then of course the shallowest node is going to be the best path, right? Because if all the path costs are constant even, right, or all the same, then the shallowest node is just going to have that depth times the path cost, and so the shallowest node is going to be the best path. But that's only if they're all the same. So here's the example, right? Breadth first search is not optimal. So if we took the first path that we found, right, that breadth first search returned, we would have a path cost of 11. But if we went further and searched a little bit harder, then we would eventually find ADEC, which was the best path. In terms of time complexity, breadth first search is pretty complex, okay? So each state has B children, right? So in a 4-directional action space, we have 4 children for each node. And consider that we have a goal at depth D, then we have to go B times B times B times B all the way. We do that D times, so we have B to the power of D nodes generated. But our space complexity is almost a worse thing, where we also have to store that entire search tree, so we have to store B to the D nodes. But you all already know that, right? That stuff is not new. Breadth first search performance is not great. But who can tell me out there what I haven't yet included in my breadth first search algorithm? Okay, we have an open list, but what are we missing? Okay, so hopefully someone out there did 3200. There's a second list. Does anyone? Hopefully someone remembers that second list. There's the open list. Someone said the visited list. Yes, so we called it the closed list in our class, but it's essentially the list of states that have already been expanded. Okay, so Bfs performance on grid. Bfs performance on a grid, and I made a little mistake here, because this is assuming we are using a visited list or a closed list. It will have space complexity equal to the size of the grid. It will find optimal paths for 4-directional movement since all costs are equal. Bfs may not find optimal paths for octagonal movement since the costs are not equal. So we can use 4-directional movement, and then we can refine the path later if we want to. Oh, I should have had this first. Okay, so this is the slide. I got these two slides out of order. So one of the most important search ideas is this idea of avoiding repeated states. So what do I mean by that? So let me go back. So when we saw in this example, we went from A to D in our search, but then we also searched back from D to A, right? So we went from A to D to A. And of course, in any environment with costs that are non-zero, right? So higher than 0. If we ever repeat a state, if we visit it twice, then our path is not going to be optimal, right? Because why would you ever double back on yourself in a path? It just doesn't make sense. It's going to be strictly worse than if you had not done that. So we want to somehow record which states we've already visited and then skip visiting them again. So that's what we're going to do now. So it's especially important in environments with reversible actions. So in reversible actions, for pathfinding, everything is reversible, right? So reversible means I can go from A to B and then back from B to A. And of course, when I'm doing paths, I can go back and forth as much as I want. So most infinite loops or wasted time can simply be avoided by not returning to identical states. And so we can remember the nodes that we've expanded and then don't re-expand them. And this can and usually does lead to exponential savings in the number of nodes that we generated. And so someone out there, 2 people called this the visited list, but we're going to call this the closed list. It's closed because we don't reopen them, right? So we're going to store states that we've already expanded. And the closed list stores expanded states. So it's often implemented as a hash table or a dictionary for efficient lookup. And we're going to check to see if a node is in the closed list or has been closed before we expand them. And the open list is sort of a fringe of unexpanded nodes, right? That's usually implemented as a priority queue based on our search algorithm, or just a queue for BFS. And the closed list is usually implemented as a dictionary. Just for those of you who are out there live, if you want to know more about this, there are multiple lectures devoted to all of these algorithms properties in the prerequisite for this course in the Computer Science 3200. So the prereq for this course is called Intro to AI. The playlist is there for you in the chat. And if you're watching this on YouTube, if you go to my channel and then you click playlists below, then you'll be able to see the playlist for that course. And there are entire lectures devoted to really going into detail about all this sort of stuff. So if all of this is like new to you and you're trying to follow along and you're having a hard time, you can go watch that course because all of the lectures are open for you. Okay. So let's do breadth first search with a queue, right? A queue data structure. And we're going to use a closed list as well. So a closed list, that's going to store states, if we remember. And the open list is going to store nodes. And the first thing in the open list is going to be a node with the problem's initial state. Okay, so then we're going to loop while true. If the open list is empty, there's no path, so we just return fail or empty path. then what we do is, this is BFS, so we're going to pop a node from the front of the queue, okay? So pop, if you're talking about a stack, it will come off the end of the queue, but the pop or the end of the stack. But when we're using a queue, it's first in, first out. And so the open list is a queue. If we pop off the queue, we get the next element, right? Not the last element. So if the state of that node is the goal, we have a solution. Otherwise, if the state has been closed already, we continue. We don't want to expand this state again. So if neither of those things are true, then we add this node state to the closed list because we don't want to come back to this state again, right? And then we expand the node and we add those nodes to the open list. And again, for those of you maybe who didn't do 3200, I go into great detail about how similar these search algorithms are. So for example, if you wanted to turn breadth first search into depth first search, all you have to do, it's the exact same algorithm, okay? Breadth first search is the same algorithm as depth first search. However, the one difference is that in depth first search, you're using a stack and you're getting the node at the end of the open list. And breadth first search, you're using a queue and you're taking the node at the beginning of the open list. It's crazy how similar all of these algorithms actually are. So if we use a closed list for breadth first search in 4 directions on a grid, this is what it looks like. So the yellow nodes here are going to be the open list, and the red states, are going to be the closed list. So initially we've just got the starting state, and we're going to just do a breadth first search out, right? So after we expand the first node, we're going to have that first node in the closed list as red, and then we have all of the initial neighbors of the children of that first state in the open list. And then we're going to loop all over those, and we're going to expand outwards, and then we can see here why some people call the open list the fringe. And it's called the fringe because it's on the fringe of the space that you've searched, right? And the closed list is kind of enclosed by the open list. It doesn't always work out so nicely visually like that, but for our case it does. So what happens, as you can see, it's going in our grid, this breadth first search is going to expand outwards and outwards and outwards, and it will eventually touch all of the nodes that are, or all of the states or cells in our grid that were connected to the starting state, okay? So that's how breadth first search works. How do we use that to compute connectivity? So as breadth first search expands outwards, we're going to mark every cell that it touches with some integer, okay? And what that integer is going to represent is the sector that cell belongs to. And so we'll call that a sector number. And we're going to store this in a separate grid, okay? And I'll show you how that works. Everything that a single breadth first search touches has a path that connects to it. Because if we think about it, right? If my breadth first search touched this, I apologize, I don't know how to change the color of my laser pointer here. So this was my initial node right here. You can kind of see this moving around. Anything that breadth first search touches, there must exist a path from that to that. So they are all going to be in the same connected sector, okay? So any two cell in the final computer grid, let me fix that. Any two cells in the final computed grid of connected sectors with the same sector number are connected. So what do I really mean by that? Well, I'm a visual learner, so I'm going to go through a visual example. Okay, so here is my connected grid. This is going to be a separate two-dimensional array that you compute, and that's the computation of the connected sectors, okay? So this is going to be a single grid that's going to hold an integer value for every cell in your grid. So you're kind of doubling your memory, but in the end, we'll have something really nice that's a consequence of using more memory. So the algorithm, in a nutshell, is going to start it's going to loop over every cell in the grid, right? So let me just move my thing down here. I'll cover up the word, no, I don't want to cover up connected. Okay, that's fine. We're missing a couple of cells up here, but that's okay. So what this algorithm is going to do, my laser pointer's not working. There we go. Is we're going to loop over every cell in the grid. How we do that is up to you, but let's just say we start in the top left and we go from the top left, we're going to go across, and then we're going to go down to the next row and we're going to go across, then to the next row and we're going to go across, etc., etc. Now, the algorithm is as follows. When I'm iterating through each cell, if the value of that cell is a 0, then it means I haven't computed its connectivity yet, okay? So if at the start everything has a 0, it means I haven't run the algorithm yet on that cell. So I'm going to say, all right, set that value to n plus 1, where n was the number of the previous connectivity, okay? So that's just a way of saying we're going to compute a bunch of different connected sectors, and the first one is going to be 1. So what I do here is I'm going to say I have a 0 here, so I haven't computed it yet, so I'm going to run a breadth first search, and everything that it touches, I'm going to give the value of 1. All right, so let's just look at how that looks. So we're going to start up here in the corner. We're going to set that value to 1, and we're going to do the breadth first search. So the breadth first search is going to go outward and outward and outward, and then eventually everything that breadth first search touches is going to be given a value of 1. And what that means is that anything with a 1 is connected to, which means a path exists, any other cell that also has a value of 1. Okay? So this one up here is connected to this one down here. This one here is connected to this one here. So if I'm playing Path of Exile, right, and I've got an NPC standing right here, and my player is standing over here, in constant time, I can say, hey, this is a 1 and this is a 1, and so a path exists between my monster and the player. And the cool thing is it doesn't matter how many monsters I have, right? I could have one here, 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 here. I could have 100 of them, and all it would do is take one lookup to find whether or not it's connected to the player. Oh my god, I drew that X exactly on a boundary. Which I didn't mean to do. So if my player's down here, for every monster, I can immediately tell whether or not I'm connected to the player, which is the first step. Okay. Now what I do is, let me discard these changes. Okay. So I just did the path for this cell, right? I was iterating over all the cells. I only made it to the first one. So let's continue with the top level of that algorithm now. We're going to go across, and if we see a 0, we do a breadth first search. But look, this is a 1. That means that I've already computed the connectivity for that cell, so I don't need to start another breadth first search for it. I keep going, it's a 1, not a 0, not a 0, I keep going and going, and look, here now I have a 0. So let me just move my camera over. So I have a 0, which means I'm going to do a breadth first search from that location outward with the next number, which is 2. So here, I'm going to start with a 2 and do a breadth first search outward until I've completed that breadth first search. Then, and what this means is anything on the map which has a value of 2 is connected, a path exists, to anything else that has a value of 2. Now I can move myself back because I'm going to do this for the rest. And so now I was right there, but I can continue the algorithm. So I'm going to say, okay, this is not a 0, not a 0, not a 0, not 0, blah, 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 blah. Keep going until I hit a 0. Okay, I hit a 0. Now let's put a 3 there, right? Because it's just the next number. So we'll put a 3 here. We'll do a breadth first search outward from there. And then we'll keep doing the same thing until we've completed this for the entire map. Okay? So now what we have at the very end is this connected sector map. That's what I call it. It doesn't have an official name. But if you want to tell if two things have a path which exists between them, so for example, this one and this one, you just compare their values in the connected sector map. And if you want to try, for example, this one and this one, even though they have the same color, right? So you've checked the color, that's the same, but you would have to go through another color to get to it. But this computes it all for you. And so this cell and this cell are not connected. And the reason they're not connected is because no path exists between them, but we can tell that now in constant time because we computed the sector map and the numbers are not the same. So this is a 2, this is a 4, therefore they're not connected. But this is a 4 and this is a 4, therefore they are connected. Now, one thing I will say about the connected sector map is that since this is going to be done for the entire grid, if we did something where we like change the grid, so let's say we had like red tiles right here and red tiles right here, right? This one would still be connected to that one. But if we made a dynamic change somehow to our level and we blocked off this one, then we may have to recompute the connectivity for everything that was connected to this cell. And in the worst case, that means recomputing the entire grid. So this is a little bit slow for dynamic changes to the level geometry, okay? So this is a pre-computed map that does not take changes in level geometry into account, unfortunately. But if you want the algorithmic description of this algorithm, I just went over it in person, or sorry, not in person. I went over it visually, but here's the algorithm for you in code or pseudocode. So we have this function called compute sectors. We're going to make a sectors grid, which is the same size as the map width and the map height, and we set that grid equal to 0. Now we have a sector number, which is equal to 0 to start with. Okay, that's going to be the number that we assign when things are connected. Then we're going to loop over the width of the map and the height of the map. And then we say if the sector value for this cell XY is not equal to 0, and if you're talking about different sizes, can we actually fit in that location? Continue. So if it's not a 0, we've already computed the connectivity, so we continue. Otherwise, if we do have a 0, then we increase the sector number by 1, and we're going to do a cardinal breadth first search outwards from the XY position with that sector number, setting that sector number as we go. Okay? And then later on, if we want to know whether or not two cells x1, y1 and x2, y2 are connected, now that is a constant time lookup, which just says, okay, return the sector value at each of those cells. So we've done a constant time lookup for if things are connected. Now, if you did 3200, you've seen all of that before, but let's take it to the next level. All right, so you haven't seen this before. Vector fields. What are vector fields? And why are they going to matter for us? So in mathematics, a vector field is mathematically, it's an assignment of a vector to each point in a space. So this happens a lot in differential equations, in vector calculus, in physics, in things like meteorologists deal with this all the time. So you could think of a vector field, for example, if you've seen like a map of the wind that a meteorologist might put out. So at every point in space, they have a vector telling you where the wind is blowing at that point. And so that would be a vector field, an example of a vector field. In game programming, what we're going to do is instead of assigning a vector to each point in space, we're going to assign a vector to each cell in our grid. Okay? Now, you do not have to use grids to use vector fields, but for this class and for this example, where, this isn't PhD work here, we're doing vector fields in a grid. And so that vector field is going to denote the designed, that's supposed to be desired, just let me fix that, discard, desired. Okay, so the vector field, once we've computed it, the vector in the grid cell is going to denote the desired action or direction of movement from that cell. So we have some vector fields in science. So for example, magnetic fields are often visualized as vector fields. Okay. So here we have this is showing you the magnetic field of the Earth, the magnetic field of a coil, and we can see here that at every point in space, we have some vector denoting where the magnetic field is pointing. So that's a vector field. In games, however, we're going to use vector fields to denote where we would want to go, right? So let's say that we have a point here in space, and we would want to know how to get to that point in space in our grid from any other point on the map. Well, that's what we're going to use vector fields for. And if you use your imagination and go back to the Path of Exile example that we did at the beginning of the class, this is exactly what we want. If we have an enemy standing right here, and another one here, and another one here, and another one here, if we have 100 enemies littered throughout the map, we don't want to have to call a pathfinding engine call and like run A star or breadth first search or whatever for that single enemy to a single goal. This is multiple agents going to a single goal. Okay? And here's what this can look like in practice. And this is what assignment 2, this is not a video of assignment 2, but it's going to be what assignment 2 can look like if you do it correctly. So here, in this example, I have the link to this online, to where this video came from. You have 10,000 particles, 10,000 particles instantaneously following the path to where the mouse cursor is. Right? And so this is a very, very powerful example of pathfinding. And what you can also notice in here is a little bit of steering behavior, right? And so they've combined vector fields for pathfinding with steering behavior for path following. And what you have is this really, really cool and powerful system, which is able to essentially pathfind as many elements or as many particles as your computer can handle in constant time. Okay, so why do I have this here? Okay, so there's a couple of steps to this. How am I going to explain this? Okay, so I think I explained this later. I apologize, I might have gotten slides out of order. There are a few steps to getting from a vector to getting the vector field. Okay, so the first step is as follows. Let me actually just do something real quick to make sure that I haven't got my slides out of order. Okay, so I know how to explain this now. So the first step is going to be computing what we call a distance map. So if you can see here, this is the computed distance map, which stores the distance from any point on the map to the given point that we want. So this would be the player in Path of Exile. This would be, you know, the rest of the level. From those distances, we're going to compute the vector field, okay? And from the vector field, we're going to compute how we actually want to follow the path. So here we can see the distance map and the vector field changing in real time as the player or the mouse cursor moves around the map in this example. And this is, your assignment is not going to look identical to this because this is not what I programmed, but it's going to be very, very similar to this, okay? We are going to have the added step of computing our own grid-based navigation mesh on top of that. And you might say, oh my God, assignment 2 is a grid-based navigation mesh. It's a distance map, it's a vector field, it's pathfinding. But the cool thing is you'll find out how easy all that is if you've been taught it correctly, okay? Okay. So that's what it looks like. Now let's show how to do it. So vector fields for games have been called a number of different things by a number of different people. Some people call them flow fields. Some people call them influence maps. Influence maps are actually they are a use case of a vector field, which we'll look at a bit later. They call them vector maps, but they're all the same thing essentially. They are very efficient structures for pathfinding in the case where you have many agents wanting to go to a single goal, which is exactly the case of a MOBA game or an action RPG. So any case where multiple NPCs need to go to a single location, i.e. the player in Path of Exile, consider using a vector field for that. It can be used to accomplish a number of tasks, not just pathfinding, but pathfinding is going to be the main thing that we're going to use it for in this course. So before we can compute the vector field, we need to first compute the distance map, right? That's the grid that we saw. So each cell of that grid will store the four-dimensional, not four-dimensional, 4D is four-directional, four-directional shortest path distance to a single goal. In practice, we will need one distance map per pathfinding destination. And we can cache those maps if necessary, for example, if the environment is static, etc. So what I mean by that is that every time your player moves to a new grid cell, you are going to have to recompute the distance map or look it up in a cached version if you have that, okay? So as the player moves around, yes, you do need to compute a new distance map. But that's the sacrifice we're willing to make in order to get constant time paths for the 200 or 300 other NPCs that we have on the screen. So here's how you compute a distance map. It's really easy. So before we looked at computing connectivity with breadth first search, but we're going to use that same breadth first search to compute a distance map. And all we have to do, instead of just marking things as true or false, whether or not they're connected, we're going to mark them with the distance or the depth of the breadth first search. So our initial node or initial state is going to have a distance of 0 because it's right at the goal location. Then we spread outward. So in our first depth of search, we mark these as 1. Second depth of search is 2. Third depth of search is 3. And what we have in the end, after we've finished that, is a distance map, okay? So, for example, in Path of Exile, if this is where our player is located, then our distance to the player is 0. If we have an NPC standing over here, and that NPC is curious about how far it is away from the player, then we know just from computing that one breadth first search that this location is 15 away from the starting location. So let's just see if any of you are awake out there in the chat. Who can tell me how I'm going to take these distances and compute the direction of movement toward the player? Who out there can tell me that? I'll keep looking while I continue the lecture. Excuse me. So that's a distance map. How do we compute the distance map? It's also computed via a breadth first search in a similar way to the connected sectors. But instead of marking each cell with the same value, we give it a value of the parent plus 1. Excuse me. And we're going to give distance map cells an initial value of -1, and any distance map cell that still has a value of -1 is not reachable from the goal. Okay? So this is different from connectivity, because remember, the connectivity map told us all pairs connectivity, right? So we did one connectivity map that said, okay, I can move from here to here, or from here to here, or from here to here. But with a distance map, we have all distances to a single goal. So if our goal changes, so like if, for example, if our player moved from right here to up here, then we would have to recompute the distance map. And in general, we want to recompute the entire distance map because reasons, but there's no real shortcut to only partially recomputing the distance map. Let's just say it. Let's call it that way. Okay. So the vector field computation, no one answered me in the chat, but from a distance map, it is very easy to construct a vector field for pathfinding. Each cell gets assigned a vector pointing to its lowest neighbors. That's it. So optional, if a cell points to both left and up, instead replace it with a diagonal left up. So let's just go look at that. What do I mean by that? Well, here's our computed distance map, right? So I know that this location is 15 away from my goal, right? So it's going to cost me 15. But watch this. In order to get the direction that I can travel, that I should travel in order to most quickly get to the goal, well, look at this. Well, my character can move up, down, left, or right. We're restricting it to 4 directional movement for now, okay? So I can move up, down, left, or right. So I will go to these places. Intuitively, if you want to get toward the player, would you go to the place that's 16 away from the player? Or would you go to the place that's 14 away from the player? Right? You're going to go toward the adjacent cell that's closest to the player. Super simple, right? So I'm either going to go here or I'm going to go here. Done. Now, if my game allows me to walk diagonally or at arbitrary directions, what I could say is instead of like maybe if I can go down or right, then how about just going down right? Okay, so what we're going to do at every location is we're going to make this computation where we draw these vectors, right? And so what we're going to see eventually is that all roads lead to Rome, right? We're all going to be pointing to the last location. So let's look at that visually so I don't have to draw it. Step one, we have the distance map, right? So over here, for example, let's say we're at the 9, right? Then we would want to point, well, we could actually go to the right, we could go to the left, or we could go up, but let's just choose one of them. And then step 2, we point to the lowest value, and then that's it. There's just 2 steps. So once we've computed the distance map, there's just one more calculation, which is computing that vector, which is just point to the direction you want to go. Super easy. And then here's how that looks. Whenever we click here and we drag around, in this example, we are changing the location, so the distance map value changes, and also the direction that you are pointing to changes. Okay, and you can see just how cool that ends up looking in terms of the vector fields, and how powerful that is, and how we can directly apply that right back into Path of Exile if we needed a pathfinding engine for that. So in terms of vector fields, the last 4 slides came from this tutorial online, so you can completely go and look at that if you want to. That's fine. If you end up taking any ideas from that for your assignment, please cite it in your assignment, but do not copy and paste code. That would be plagiarism. Okay, before we end it out, I want to show you some performance notes on this and how theoretically we can't change the performance of things like BFS, right? That's set in stone because of math. But practically, we can change the performance, and we can make it run many, many times faster than if we implement it naively. Okay, so actually implementing BFS iteratively with a queue results in poor performance. And why is that? It's because vector implemented queue needs to left shift all elements in order to pop from the front, which can be very slow in practice. And so performing lookup in a closed list can also be slow if implemented poorly. So what do I mean by this? So let's look at this example. A vector implemented queue needs to left shift all elements to pop from the front. So if we have our queue, and I apologize for my handwriting here. So if we have a queue, right, this is going to be implemented as a vector because vectors are contiguous, which is great for cache coherency, etc. So we're going to have our queue, and it's going to have a bunch of things in it. All right. So the queue is, whenever we call pop, is going to take the thing from the front of the queue, and it's going to then delete that element. Okay. But it can't just erase it magically, right? Memory can't magically be erased, especially in C++. So what has to happen in order to delete the first element, it's not actually deleted. What happens under the hood is that the second element overwrites the first, the third overwrites the second, the fourth overwrites the third, Okay, so in practice, when you think you are just taking something from the front of a vector, you are actually shifting everything else in the vector to the left by 1. And that is horrendously inefficient, okay? Also, let me get rid of these annotations. Performing lookup in a closed list can also be slow if implemented poorly. So what do I mean by that? Well, here's another example where, let's say I have my closed list, and that's, if I implement that as a vector, right? So maybe I have a few things in the closed list here. Like this is like 1, 2, I visited that, and 3, 4, and like like more things in here. By looking up in the closed list, I'm going to be basically iterating over this whole vector and saying, okay, let's say I'm looking for 5, 6, right? Is 5, 6 in the closed list? Well, I would have to look here. No, it's not there. Then I look here. No, it's not there. Then I look here. No, it's not here. Maybe it's not there. Maybe it's the first element. And so that's another linear time operation. So deleting from a vector, linear time operation. Looking up in a vector, linear time operation. We want to eliminate all linear time operations if possible. So here's how we can avoid the queuing problem of deleting something and then left shifting in order to implement a breadth first search. So we're going to simulate a queue using a vector, but we're not going to be doing any deleting. All right, so this is another example of a cool optimization you can do where you're trading memory for speed. Okay. To insert into the queue, you're going to push the state into the back of the vector as normal, right? Because you insert into a queue, it goes to the back of the queue. First in, first out. However, instead of removing from the front of the queue, what you're going to do is you're going to have an index pointer to the front of your imaginary queue. And I have a visualization of this, so it'll be easy. So instead of checking to see if the queue is empty, right? So we need to be able to push things, we need to be able to pop things, and we need to be able to check if the queue is empty, right? So those are the three operations that we need for a queue. So here is how you could do breadth first search with a vector as a queue. So here is our initial state. Let's say we have a vector with one thing in it, okay? So we've put one thing into our queue. This is the easiest possible case. It's where we start. Now, what we have is we're going to have this green. Oh, I apologize for colorblind people, okay? So the top one here, if I say green, I mean the top one. If I say red, I mean the bottom one. So the top arrow is going to be pointing to the front element of the queue. Not the front element of the vector, but the front element of the queue that we're simulating with a vector. The red arrow is going to be pointing to the back element of a vector, okay? So if we put one thing in, then the front and the back are identical, right? So this is nothing right now. Now, let's say we are going to push three things into our currently empty queue. So what I've done is I have put three things into the queue, and I've taken one thing out of the queue. So I'm going to take one thing out and put three things in. So I put three things in. That's really easy, right? I just put one thing here, one thing here, one thing here. So 1, 2, and 3, okay? Now, if I take something out, instead of taking it out and then shifting everything to the left, what I do is I use this index as a pointer, if you will, to where the current front of the queue is. Okay? So instead of having to delete anything, I leave those things into the vector and I just point to the current front of the vector or the front of the queue. So let's say I'm going to do another round of inserting and deleting where I'm going to delete this element, right? I'm going to pop this element from the queue, pop, right? And then add some more things to the end. So here's what that looks like. I've popped that thing from the queue, but I haven't actually done the delete operation on the vector. So the next thing in the queue, I've just incremented that index by 1. So as I keep popping things from the queue, what I do is I keep incrementing the front of this, I keep incrementing the index to the next thing. And so in order to tell if my vector is ever empty, right, if my queue is empty, so right now I can tell that I have 5 things left in the queue. Well, how do I know that I have 5 things left in the queue? Here I had 6 things left in the queue, right? It's because the difference between the end pointer and the current front pointer, that is the number of things left. So if I keep going, and if at some point my front pointer is equal to my end pointer, then I know that the queue is empty. Okay, so that's how I can tell. So this is an optimization that you can implement if you want for the assignment. You will come nowhere near so for all my assignments, I like to have like timing operations to see if you can like come close to my speed. So I've released a solution executable to you so you can see how fast my code runs. But you will come nowhere near that speed if you don't use these sort of operations. Okay, so try and get as close as you can to my speed on the assignment. But what we're doing here, as you can see, right, if we were just using a queue, a normal queue, here we would just be storing these 5 elements, right? Here we would be storing no elements. But when we're using this speed optimization, we have to use more memory because we're never deleting anything, right? So we are trading memory, we're using more memory, but we're going way, way faster. Okay. Another optimization that you can do for the closed list, and we did this optimization for 3200 assignment 2 as well. So this may come as no surprise to you, but we can use the distance maps values as a constant time closed list query in lieu of using a vector or a set for checking that. So initially, we're going to assign distance map cells values of something like -1, so some unique number, and any state which has not been visited yet is going to still have a value of -1. So if we want to query a state that has already been seen by the BFS, instead of having a closed list vector that we add things to and we check it linearly, what we can do is just query the distance map and say, hey, distance map, what is the value? And if the value is not -1, then it has already been visited. So if you can't do this, you could use a separate Boolean grid if you want to. But this is what this means. Okay, here's a visualization of that. If I'm at some point in my breadth first search, then at some point I want to check, have I visited a state yet? So I don't need to keep a vector or a running collection of all the states I've visited, because anything that I have visited has a non-1 value, right? So anything that I've visited is going to have a value which isn't -1. Anything that has -1 hasn't been visited yet. So I can shortcut and not need the extra data structure of a separate closed list. But if you can't get this to work, you should be able to, but if you can't, you could also view this as a secondary closed list Boolean grid in which you mark things that you've visited as true and things that you haven't visited as false. Okay, so that's the same thing. This grid of falses being -1s and trues being everything else is equivalent to that. And just at the end here, I want to mention influence maps. So influence maps, they typically incorporate other logic than just distance to the goal. And so some gameplay desire is going to have influence over your movement and over your actions. And so influence maps have a desired influence of some sort of gameplay mechanic that is not just distance to a goal. And they can be used when it can be difficult to construct an objective function for other algorithms, for example. So some examples of influence might be keep distance from obstacles or enemies, avoid attack damage from enemies, or any other combination of things. So let's do an example of an influence map. Let's say that we have a goal over here, and we have a start over here. So we've computed a distance map which avoids stepping on this enemy tile, or if it's like a trap on the floor or something like that, right? So by not assigning values in our distance map, we have essentially made this influence map. This is a very basic example where we avoid a tile, right? That's the simplest possible influence map. Let's say another example where we have like a boat moving through water, and maybe the shore has like shallow water. So we can pathfind through it, but we don't want to get so close to the shore that we risk hitting the water, right? So what we can do is we could say, have an initial influence map, which is set to say 10, for example. And what that's going to do is we're going to add 10 to every value in our distance map. And so then when we go to do our distance map, now we have an influence map, and the influence is repelling people from going to the shoreline, right? And the reason it is because when we go to make our vector field, well, we want to go from this cell value to the lowest cell value, so we're not going to be going toward the shore unless we absolutely had to, right? That's another example of influence. And we could do something with like multi-influence. So let's say down here at this E, we actually have like a turret, okay? And the turret is going to maybe be able to shoot players that walk into some radius within that enemy. So what we could do is give that some huge negative influence, right? So maybe 50. And then when we do our pathfinding for that, we will really want to avoid taking any damage here, right? So what we've done here is we've basically said maybe taking 50 damage or sorry, instead of taking any damage, we would want to go 50 distance more. So these influences, you have to come up with these numbers and what these intuitively mean within your AI design system. So here's an example of an influence map in practice where, what is this one? Finding a safe spot. So these NPCs are exerting a negative influence on this. So the NPCs are in red, the player is in blue, and I guess they're all NPCs because it's guided by AI. But you're just trying to find a safe spot which is not near these things which you don't want to be near. And you can see these influence maps sort of pushing the user out of their influence, and it's avoiding them in real time just using these influence maps. You can also have things where you have like people attacking and people defending. So here, for example, maybe you have these attackers in red, and you have these blue defenders which want to go toward areas where attackers are overlapping your nexus or something in a MOBA. So here you can see that when the attacker's influence is overlapping or coming near, oh my god, my face is so red. That's hilarious. Let me switch to this. You can tell my screen is the thing lighting my face because it changes with that. So let's go back. So yeah, these defenders are trying to go to areas where the enemy's influence is overlapping their goal, which is maybe their nexus or their home. Okay, so that's an influence map. We're not going to be doing those like in the course, but I just wanted you to know what they are and how they could be used, because, you know, this is all about practical implementations and practical things you could actually use in your game AI. So that's it for this class. Next class, we're going to go over all of assignment 2. It's going to be a super fun assignment, and I think you'll have a lot of fun doing it, and I'll have a lot of fun marking it and seeing what sort of cool things you come up with. So that's it for this class, and I'll see you on Tuesday.